All right, so where did we stop last time? I believe we were talking about the various ways we can represent. Yeah.
Sorry, I actually have a question.
Mhm.
Where can you find the worksheets?
They're in the lab manual.
Oh, okay.
Yeah, so if you go into the lab manual for the class, look at experiment 1, and you'll see the pre-lab part of that are those 3 tables that we looked at in lab earlier today. Okay, and remember, just for the record, y'all are doing Form A. All right, it says that on the submission instructions in Canvas, but just to reiterate, you guys are doing Form A. You don't need to worry about doing B and C, only A. All right. Okay. So the last time we met, we were talking about ways of representing molecules in a structural form. So I think we talked about how, a lot of times in Gen Chem, you tended to just to represent compounds in their molecular formula. And that worked for Gen Chem because most of the things you were working with there were ionic compounds that can only combine in one set ratio. However, with organic molecules, for a given molecular formula, you can have many, many possibilities, right? So for C5H12O, I could probably come up with, off the top of my head, at least 5 different compounds that have that same molecular formula. So it's rather ambiguous for us to use molecular formulas to represent compounds in organic chemistry. So instead, what we will always do is represent our molecules in some form of a structural formula. And so we talked about these at the end of the lecture last time. So the Lewis dot would be an example that we're all familiar with. However, the Lewis dot structures are rather tedious to draw out. They take up a lot of space. It takes up a lot of time to draw all of those bonds in, especially if you're dealing with a larger molecule. So we don't typically use Lewis dot structures. What we will use more often are one of these condensed or shorthand ways of representing the molecule. Now, we looked at the condensed structural formula last time. We kind of went back and forth between Lewis dot and condensed. Condensed is fine, but sometimes it takes you a couple minutes to kind of figure out exactly what's connected to what. So a better way would maybe be the partially condensed structure, because that actually pulls out branch points. It pulls things out of that straight chain that are not part of the main chain, right? It shows you specific branching points in the molecule, which just makes it a little bit more easy to see what's going on. But by far, the most common way that we will start representing our molecules in this class is the line angle. This is the zigzag thing, okay? So that's what I want to spend, because this is going to be an incredibly important part going forward. I want to spend a bit of time practicing how we can go from a Lewis dot structure to this line angle form, okay? Because again, this is the way we're going to start representing molecules from here on out, all right? So if I were to represent this structure, this 3-methylbutan-2-ol in a line angle form, the thing I like to do is consider first what I will start calling the parent chain or the main chain. All right, so when I say the parent or the main chain, what I'm talking about is this longest contiguous carbon chain. So in this particular molecule, that would be a carbon chain of 1, 2, 3, 4. That would be what I consider my parent or main chain. And so I'm going to draw that first, and then I'll worry about putting the branches on. All right. So if I'm just drawing a 4-carbon chain, well, that's just going to be a zigzag with 4 points. Right. So it would look like this. There's 1, 2, 3, 4. That is a 4-carbon chain in the line angle form. Now, we're not done, because we certainly have in this molecule more than just 4 carbons bonded together. Okay, we have those branch points. Specifically, you have an OH group off of carbon number 2 And then you have the methyl, or this CH3 group off of carbon number 3. And I need to indicate that in this line angle form. And so I'll handle the carbon branch first. Let's talk about this CH3 group. Now, again, you want to pay attention to where you're going to put that. It is off of carbon 1, 2, 3. So I'll find 1, 2, 3. I'm going to indicate that there's a 1 carbon branch off of that C3 position. And since it's just a CH, I can do that with just putting a line. Right? Remember, anytime you have a line, that represents a carbon. So I'm just going to do that. And this point right there represents a 1 carbon group. Right? That represents that CH3 that is right there. The second branching point I have off of my parent chain is off of C2, and that's the OH group. Right? So then I find C2, 1, 2. Off of this position, I need to put an OH group. Now, would that be correct? No. I mean, it's a viable structure, but it's not that structure. Right? If I just left it as is, this would indicate there's a CH3 up there. Okay, I don't want to indicate that because that's not what's there on C2. What's on C2 is an OH group. I have to put that in explicitly. So I will simply write OH. And that would be the line angle form of that 3-methylbutan 2-ol compound. All right. Questions there? Okay, so let's go ahead. Why don't you do this one? So you're going to have to do 2 things here. First, you're going to have to figure out what's going on with the bonds. Draw out the Lewis structure of that. And then you're going to convert the Lewis structure to the line angle. Take just a couple minutes and see what you can come up with for that. All right, so the first thing that we're going to do is just kind of draw out exactly what the condensed structural formula shows. All right, so I think I've got the right number of carbons. Let's make sure. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5. Okay, so we're good. Now, then you want to verify, does everything have the proper valence? The way I have it written, no, we're not good. These carbons don't have the right number of bonds. And for that matter, neither do those 2 carbons. So how do we fix that? Yeah, the easiest way of fixing it is just by starting to put multiple bonds. So I think to fix these guys, put a triple bond between them. That would make those 2 happy. So each of those carbons now has 4 bonds and they're satisfied. What do you want to do about those 2 carbons? They don't have the right number of bonds. How can we fix that? Yep, with a double bond. All right. So now all the carbons are satisfied. They have their correct valence. Now what we want to do is translate that into the line angle form. And now again, what I like, so this one doesn't have any branches on it. So it's basically just going to be kind of a straight chain in a sense. See that chain, but nonetheless. So I think the way I would start this anyway is just by putting a 1, 2, 3, 4, 5, just draw a zigzag with 6 points. Okay. So let's do that. I'm going to draw out my parent chain, 1, 2, 3, 4, 5, 6. There we go. Now, that's not correct because this indicates that this whole 6 carbon chain is connected through single bonds, which is not what is reflected here. So we've got to add in those multiple bonds down here. So what we see is that we have a triple bond at carbon number 1 at carbon 2. So I'm going to go ahead and put that in. There's carbon 1, there's carbon 2. So I need between carbons 2 and 3, I need a triple bond right there. All right. So there's my triple bond. Then we have a double bond at position 1, at position 4. So I need to put that in as well. 1, 2, 3. There we go. So that is more or less correct. I say more or less correct because most people do not show triple bonds this way. It's kind of like an angled way. If you think about it, a triple bond does not have that kind of bond angle. The triple bond is linear. So what most people would do is something like that. Right? So now between carbons 2 and 3, notice the bond angles are actually more accurate to real life, the linear bond angles. But if you had put this as your answer, I'm not going to count it wrong. There is, yeah, go ahead. Because these are sp2 hybridized carbons, so those do have, that does kind of accurately reflect the bond angles for sp2 hybridized carbons. Yeah, that's because remember the sp2 hybridized carbons have 123 bond angles. And so we would expect those to be kind of angled. Now, there is a slight twist here that I didn't mean to put in here when I gave you this example, but notice the double bond, how the H's are kind of going in the same direction as each other. If I were to think about where my H's are here, you have an H going up and you have an H going down. So the H's are actually going in the wrong direction from each other relative to what's shown here. It's a little bit beyond where I wanted to go with this problem, but the better answer would actually be something more like this. Because now you have an H going there and an H going there. They're going in the same direction as each other. This gets into a specific class of isomers called stereoisomers that we'll talk about shortly. But that would be the better representation of this. Exactly. Yeah, so when we get to double bonds can be either in a cis or a trans orientation. And that depends on how the H's are relative to each other, if the H's are going in the same direction as each other, or if they're going in opposite directions of each other. And so we'll talk about that a little bit more later today.
Just have drawn the H down, the second one down.
You mean up here?
Yeah, why does it need to be up?
Yeah, I mean, that's what I probably should have done when I drew out this. I mean, it could exist in either way. It could exist this way, or I could have, instead of having that drawn up, I could have drawn it down that way. That would have been the trans version of the double bond. So yeah, it's just different forms of the double bond.
Okay, even if you use the very left line drawing.
Yeah, for now, if I gave you that and you gave me that, I would count that as correct.
I just I didn't see the triple bond being straight, but again, if you would have just drawn the H down, I wouldn't have to change it that way. I would have just kept the original drawing.
Yeah, I mean, if what I had given you was that's this orientation of the double bond. No, if you were just given this, you would have no idea. This is a little bit ambiguous. This way of representing the double bond does not tell you whether the H's are opposite each other or whether they're going in the same direction as each other. And so when I went, since that's what our starting point was, whenever I went over here, you could do either one. Because again, this structure does not tell you what forms of double bonds it is. So I just, whenever I drew this out in its Lewis structure, I arbitrarily put the H's on the same side, or cis, as you would call it. And so that's why, based on my original Lewis structure, this would be the right way to do it. But based on this Lewis structure, this would be the right way. It's two different forms of a double bond. And again, we'll get more into that later today. But let's go ahead and try one more of these. So do the same thing here. Take that condensed structure formula, convert it to its Lewis structure, and then convert that into a line angle. So here's my first stab at the problem. We've drawn out the parent chain. Pulled things out of the parent where I think it's appropriate. But are we satisfied with what I have so far? your carbons. 4 bonds, 4 bonds, 4 bonds. Oh, 2 bonds. That's not right. Now, in the past, what we said is that you could fix valences oftentimes by making multiple bonds. So could I put maybe a double bond to that carbon? No, because then that one would have 5. Similarly, I can't put a double bond to the oxygen either. Because remember, oxygen always has 2 bonds and 2 lone pairs. This oxygen, the way it is, already has 2 bonds. It can't take any more. What's my other option? Yeah, exactly. Yep. So remember, especially when you're dealing with heteroatoms, that's a very common thing to do. Pull them up out of the parent chain. So if I do that, so I'm going to put the oxygen here. Well, that's still not right because neither the oxygen nor this carbon have their correct valence. And so each of them need 1 more bond to be happy. So that works out well. Just stick another bond between them. I think that should do it. Everything's good. Everything has its proper valence. Okay, so now we figured out the structure. Now we just need to convert it into the line angle. And again, the way I would approach these is to start by drawing the parent chain, the main chain. This has 1, 2, 3, 4, 5, 6 carbons. So I'm just going to draw a zigzag with 6 carbons. 1, 2, 3, 4, 5, and 6. Now we can start decorating it. So off of carbon 2, you have an NH2. So I'm going to indicate that. All right, so there's that. Then what? Off of carbon 3, you have a 2-carbon branch. So I'm not going to draw that explicitly because we're just dealing with CHs. So I can abbreviate that with points, right? So I'm just going to draw kind of a 2-point thing off of carbon 3. So that would be the CH2. That would be the CH3. What's that?
By that direction, it's the very bottom stick.
Oh, I could have angled it that way as well. Yeah, either way. Because remember, this bond right here is a single bond, so it's freely rotating.
So it generally doesn't matter, or just doesn't matter now. But in the future, will it matter?
Not with single bonds. Yeah. And then what do we have? On carbon 1, 2, 3, 4. That's where you got the double bond oxygen. And then finally, off of carbon 5, you have another 1-carbon group. So I'm just going to draw a stick coming down. There you have it. Questions there? Yeah.
So for the CH2, CH3, we just know like the first one is CH2. It's like I thought one line or like one end of the line is CH3, right?
Yeah, anytime you have the end of the line, it's where it's not connected to anything else, that's a CH3.
And then like that little corner edge, yeah, that one.
Mhm.
That's CH2.
Yeah, because the reason why is because remember, all carbons make 4 bonds. So this carbon here, the one in question, is making an explicit bond to the parent chain, that's 1, and an explicit bond to the end. That's 2 explicit bonds that it makes, but all carbons have to have 4. So whatever bonds are not explicitly shown are assumed to be to hydrogens. So the remaining 2 bonds that that carbon needs are to hydrogens, thus making it a CH2.
Are those pairs not?
It's kind of optional. A lot of, like, if you were just drawing the molecule kind of by itself, like we're working with this today, a lot of people wouldn't bother drawing in the lone pairs. But if you were going to draw a mechanism involving this, kind of like what we did on day 1 with the arrows and showing that this electron went to attack this position, I probably would show the lone pairs there because they're actually going to be doing something. So yeah, it's kind of optional with the lone pairs. If I just gave you a problem on your Gen Chem review quiz that said, convert this to line angle form, and you did not show the lone pairs, I'd be fine. All right. Okay, let's do one more. Okay, so I'm going to start this one the same way we start the others, which is draw out the parent chain. The slight difference in this one is, notice you have an oxygen embedded in the main or parent chain here. You have to show that. All right, so we're going to have a zigzag line and then an oxygen and then the rest of the zigzag line. So this is going to be 1, 2, 3. One, 2, 3. So notice it's that 1, 2, 3, 4th position of the oxygen. So I have 1, 2, 3. This next position is going to be my oxygen. So there's kind of the skeleton of our structure here. Notice up top you have 1, 2, 3, and then oxygen. 1, 2, 3, 4. Make sure we have that in this. 1, 2, 3 oxygen. 1, 2, 3, 4. So that is correct. Now we start decorating. Off of carbon 2, you have this 3-membered ring. Now, in line angle form, any of these rings like that are simply going to translate to polygons. Right? That is a 3-membered ring. So we're going to stick off of carbon 2. We're simply going to stick a triangle off. And this triangle represents that 3-membered ring. Next, off of carbon 3, you've got that C double bond up. Then we've got our oxygen. Got a CH2, then you've got a CH. This one should have a methyl stick or a CH3 sticking off of it. So it's going to draw a line. Yeah, a 1 carbon group. So like you have CH4, the molecule CH4, that's methane. All right. So it's a molecule all by itself. But if you have a one carbon group hanging off, you don't call it a methane because it's not a molecule all on its own. You kind of drop the suffix and add YL. So methane is a standalone molecule. Methyl is the one carbon group. And then lastly, on that terminal carbon, you have a triple bond to nitrogen. So that would be right here. I'm going to just stick a triple bond in. Well, so this one has the right angle to it. The 180 degrees refers to the angle between here, here, and here. So that is all straight and along. Okay. Yeah, go ahead. Mm-hmm.
Is it H2C because C has to be touching above
Which one?
H2C instead of CH2?
Oh, that's the reason I have it shown like that is because this carbon is bonded to the other two carbons.
Right.
If I were to write it as CH2, it would look like the H's are bonded to those other carbons. So that's why I have it like that. Just to clearly indicate that it's the carbon that's bonded to those other two carbons. Any other questions on this going from Lewis to line angle? Okay, so you'll get plenty of practice going forward because like I keep saying, this is the way we are going to start representing all of our molecules. All right. Okay, let's talk a little bit about resonance. So we already did a little bit of this in lab earlier. I kind of showed you that example of that one compound, that acetanilide compound in lab that you're going to be working with. Looked at a resonance form of it. So let's go ahead and talk about resonance. So some molecules, especially molecules that involve pi bonds and lone pair electrons, a single structural formula is just not sufficient to describe what the true molecular structure. And so when you have molecules that have pi bonds and lone pair electrons, you will almost always have different resonance forms. Now, one thing to be aware of here before we even start trying to draw resonance forms. When I say a resonance form, what I'm referring to is a lot of times, I think maybe a better way of calling that is a resonance hybrid. So it's not like, so I've got the three different resonance forms of that compound shown. It's not like this structure is sometimes like this and sometimes like that and sometimes like that. It's not flipping between the three. It is a hybrid of the three. It is a blending of the three. So in the same way that if you take the color red and you mix it with the color blue, that's how you get purple. So if you look at a purple object, it's not sometimes red and sometimes blue. It's just a mix of those two colors that is always purple. That's kind of the way resonance works. Another way, try to get this right. Like animal husbandry is not so great. But like, what is it? A mule? Is it a mule that's a cross between a horse and a donkey? Okay, so yeah, if you look out in a field somewhere and you see a mule, it's not like that half of the time it's existing as a horse and the other half of the time existing as a donkey. It's always a blend of those two animals, right? It's kind of the same thing, right? These resonance hybrids don't flip back and forth between each of the structures. They're just a blending or a mixture of the different resonance forms, right? So that's just one thing to be clear of there. Now, when going from one resonance form to the next, you cannot touch the sigma bonds. Right? What I mean by that is I can't say, oh, well, I need to draw a resonance form with this. Let me just switch the carbon and the sulfur and call that a resonance form. That is not a resonance form. That would be a different compound. That would be a different connection of atoms and thus a different molecule. The only thing that you can move when trying to do resonance are lone pair electrons and pi bonds. You can't touch the sigma bonds. So compare these two. Notice what has changed. Kind of the most apparent thing to me is the carbon to nitrogen was originally a double bond. It is now a triple bond. Well, how did we get that new bond? And notice what else has changed. This nitrogen did have a lone pair of electrons. It is no longer present. The reason why the nitrogen doesn't have the lone pair electrons anymore is because the way we got that triple bond is we pushed this pair of electrons into the carbon to make that third bond. So to kind of illustrate this with arrows, the way we go from form A to form B is this lone pair on nitrogen gets pushed in to carbon. Now, notice what else? I cannot just make a new bond to carbon and leave everything else as is, right? Because this form has two bonds of sulfur. And if I just put a third bond from nitrogen to carbon and left everything over on this side the same, that carbon would have 5 bonds, which it can. So if I'm going to make a new bond to carbon, one of these guys has to break. And that's what you see over here, right? Now, instead of having a double bond to sulfur, it's a single bond. And so to indicate that, I'm going to have an arrow saying that the pi electrons between carbon and sulfur are going to break. And those two electrons making that pi bond are going to end up on sulfur alone. So that's why you'll notice sulfur originally had 2 lone pairs. Over here it has 3 lone pairs. Could you draw the arrows to indicate how we get from B to C? Like to start at an end. But compare B and C. Over here, we have a carbon sulfur single bond. Over here, we have a carbon sulfur double bond. So what that means is one of the lone pairs on sulfur here is going to get pushed into carbon to make that second bond. That also makes sense if you look at your lone pair electrons. Sulfur has 3 lone pairs here, but it only has 2 lone pairs there. That is because we use one of these 3 to push in carbon to make that second bond. So indicating that with arrows, I'm just going to kind of go the opposite direction that I just did. Now again, I can't just put a second bond of carbon and leave everything else as is, because if I did that, then the carbon would have 5 bonds on it. So as I form a new or a second bond from sulfur to carbon, I'm gonna have to break one of those bonds from carbon to nitrogen. And this arrow is indicating that one of those pi bond electrons, the 2 electrons of the pi bond, are being pushed now into the ring of the nitrogen. While you have 2 bonds there. Now again, it's kind of a cascading effect at this point. If I can't just put a second bond between the ring and the nitrogen, because then that carbon would have 5 bonds on it. So as I make the second bond between the nitrogen and the carbon, I'm going to push those electrons over here. And then finally, a pair of electrons that with this bond end up directly on that part. You see that shown. Okay. So the important thing to note, this is a little bit of a complicated resonance example, especially going from here to here. But the important thing to know is that when you're drawing resonance forms, the only thing you can move are lone pair electrons and pi bonds. Now, the charges. How did I know that this nitrogen is neutral, whereas this nitrogen is positive? First off, you know your normal valences. I know if nitrogen is making 3 bonds and have a lone pair, that's a neutral nitrogen. So that's how I know that that one has 0 charge. Same thing with carbon. I know carbon always has 4 bonds. This carbon has 4 bonds. It's a neutral carbon. Okay. So you want to make sure you know your common valences for the various atoms. Beyond that, how do I know that once I made this type of a structure, the nitrogen is going to have a positive charge? That is what we refer to as formal charge. So the way you calculate formal charge is you consider the valence electrons of the particular atom. So you take the valence electrons, and then you subtract the number of lone pair electrons. And then you subtract half of the bonding electrons. So let's do the nitrogen, that nitrogen in structure B. Let's prove that this is actually right, that it actually is a positive 1 charge. So we're going to calculate, essentially we're just going to calculate the formal charge of the nitrogen in this species. So take the valence electrons. How many valence electrons does nitrogen have? 5. And then we're going to subtract lone pair electrons. Well, doesn't have any lone pair electrons, so that's a 0. Minus 1/2 of the bonding electrons. So that nitrogen has, in terms of the bonding electrons, 2, 4, 6, 8. That nitrogen has 8 electrons in bonds. So 5 minus 1/2 of 8, that is +1. Yeah. Yeah. So the formal charge formula is down there. So valence electrons. We want to ask ourselves, how many valence electrons does nitrogen have? Well, you can look at the periodic table to figure that out. Nitrogen is in the 5th group on the table, which means it has 5 valence electrons. So that's where that 5 came from. Then we say we subtract half of any lone pair, or sorry, we subtract the lone pair electrons. That nitrogen does not have any lone pairs. Right? You don't see any dots surrounding that nitrogen. So that's why I put the 0. That nitrogen has 0 lone pair electrons. Then we subtract half of the bonding electrons. This nitrogen has 4 bonds surrounding it. Right? 1, 2, 3, 4. Each bond has 2 electrons. That's a total of 8 bonding electrons surrounding that nitrogen. So that's why we say 1/2 times 8. Let's do another one. Why don't we do, let's prove the sulfur here. Let's prove that this sulfur actually does have a -1 formal charge. Let's see. So we'll start with the valence electrons that sulfur has. How many valence electrons does sulfur have? That should be 6. Minus the lone pair electron. Well, in this resonance form, sulfur has 2, 4, has 6 lone pair electrons. So that's going to be 6 minus 6. Minus 1/2 of the bonding electrons. There are 2 electrons in that bond, so that would be minus 1/2 of 2. And lo and behold, 6 minus 6 minus 1/2 of 2 gives us a -1. Mm-hmm.
Check to be sure that order is in.
Mm-hmm.
But then how is it that since electron, the negative charge?
This one here?
Yes.
Well, let's go ahead and do the formal charge of this one. Okay. So remember, there is, so just to be clear, in this ring, each of the carbons of the ring has only 1 hydrogen. Okay, so maybe we'll do this. All right. So I'm just trying to explicitly show the bond so we don't forget about that. All right, this carbon here is making 3 bonds and has 1 lone pair of electrons. Can we agree on that? Okay, so once we agree on that, then it's just a matter of following this equation again. All right. What is the valence? How many valence electrons does carbon have? 4 minus the lone pair electrons, which there are 2, minus 1/2 of the bonding electrons. Well, you've got a bond to that carbon on top. You've got a bond to the carbon on bottom. And you've got a bond to the hydrogen. So that's a total of 6 bonding electrons. And what does that give us? 4 minus 2 is 2. 2 minus half is 6. That would be a -1. So that's why it has a negative charge. Questions there? All right, let's do another example of this. Oh, by the way, actually, before we do, one point that I should make, not all resonance forms are created equal. What do I mean by that? Well, I already told you that this species exists as a blending of those three, as a resonance hybrid. But not all of them contribute equally. It's not like it's a third this, a third that, and a third that. Because some resonance forms are better than others. When I say better than others, what I mean by that is more highly contributing. So I want to give you some guidelines for that, for picking out which resonance form is better than others. Good resonance forms have octets on all atoms and small charges. Ideally, 0 charges. But if you have charges, the smaller the charges, the better. So it would be better to have a +1 and a -1 in your resonance form than a +2 and a -2. You want your charges to be as small as possible. Okay. If you have the same types of charges in 2 different resonance forms, you want to make sure the negative charge is on the more electronegative atom. So let's look and see if we can figure out with these 3. Which of these 3 would be the best resonance form? Yeah, it's going to be A, because A has 0 charges. That's kind of the first and foremost rule. Neutral resonance forms are better than charged resonance. So A has no charges, so it's going to be the best. All right, now what's second? Well, this one has a +1 and a -1. This one has a +1 and a -1. So we have kind of equal charges, the charge distribution in both B and C. So when that's the case, that's when we want the negative charge on the more electronegative atom. So that boils down to what's more electronegative, sulfur or carbon? Sulfur. This would be the second best. This would be the worst. All right. Questions there? Mm-hmm. Yeah, the stability, and thus because it's the most stable of those forms, it's going to be the most contributing of those 3 forms. Saying it another way, this compound is going to look most like this. All right, let's look at one more example of this, because this is sometimes a little bit tricky for people sometimes. So what we want to do is draw 3 resonance forms of this ion. And then we want to choose the best form. All right, so I'm going to go ahead and draw one resonance form of it, and then you can come up with the other 2. So our starting point here will be okay. Now, by the way, just as a reminder to you, the sum of the formal charges have to equal the overall charge of the species. This is a -1 ion, which means in all resonance forms, the sum of the formal charges have to be -1. Now we can you don't necessarily have to do the formal charges of every single atom in every single resonance form. Now, the reason I say that is because we know what the normal valences of atoms are. Look at the carbon, for instance. Is that carbon in its normal valence state? Yeah, because it's making 4 bonds. And all carbons should have 4 bonds. That tells us that's a 0 formal charge. So I don't really need to. The point I'm making is if you know what your normal valences are, it can save you a lot of time. I can just look at that and say, oh, well, that's carbon in its normal valence state. That's a 0 formal charge. I don't have to go through that calculation. What about the oxygen? Is the oxygen in its normal valence state? 2 bonds and 2 lone pairs. Looks good to me. That's a 0 formal charge. The nitrogen's not in its normal valence. But a normal nitrogen should be making 3 bonds with 1 lone pair. This does not have that. What does a nitrogen have? What does a formal charge of nitrogen have to be? Remember, it has to be -1. And we know that because we know the sum of the formal charges have to equal the overall charge. We've already established that's 0 and that's 0. By default, the nitrogen must be a -1 because the sum of the formal charges have to be -1. If you didn't know that, or if you weren't comfortable with that, you could have certainly gone through that calculation here. Nitrogen has 5 valence electrons minus the lone pairs, 5 minus 4, minus half of the bonding pair electrons, 2, 4. 5 minus 4, minus half of 4. That's -1. So, however makes more sense to you. All right, so let's go ahead and see if we can come up with a different resonance form. Remember, all we can move are lone pair electrons and pi bonds. So basically what our 2 choices are, do you want to push lone pair electrons from the nitrogen, or we can push lone pair electrons from the oxygen? Those are the only 2 choices. If we push lone pairs from the nitrogen, we're going to do something like this. And that's going to break one of those. So now we have 3 bonds between nitrogen and carbon, and only 1 bond between carbon and oxygen. We can go through and assign formal charges now. Again, the way I would look at this, I would look at each of these atoms and say, are any of them in their normal valence states? Carbon, that has 4 bonds, that's normal. It's 0 formal charge. Nitrogen, making 3 bonds with a lone pair, that's a normal nitrogen. It's a 0 formal charge. Here we go again. You could go through and figure out what the formal charge is on oxygen, or you could say, well, I know the sum of all 3 formal charges has to equal the overall charge. That's 0 and that's 0, and the sum has to be a -1. The oxygen's got to be -1. Or again, you could just go through that formal charge calculation for this and prove it. Third resonance form, we're going to push from the oxygen in. Okay, so looking for normal valences. Oh, this overall is a negative, by the way. Carbon has its normal valence, 4 bonds, formal charge 0. The other two are not normal. So I'm going to have to go through and I think do formal charge calculations for these two. So the oxygen formal charge. Oxygen has 6 valence electrons minus the lone pair. We got 2 lone pair electrons minus half of the bonding electrons. 2, 4, 6. Plus 1. What does that tell you this nitrogen has to be? Yeah, it has to be -2 because again, the sum of the formal charges have to equal. Or you could go through and do the formal charge calculation if you'd like. Prove it to yourself. Okay, so now we've got our 3 resonance forms. We've identified the formal charges in each. Let's rank them. None of them are neutral. So next, we want the formal charges to be as small as possible. So you have a 0, 0, -1, a 0, 0, -1, and a 0, -2 plus 1. So that's not great. I'm going to call that my worst. But between these two, the first two, it's the same numbers, right? Same magnitude of charges, 0, 0, 1, 0, 0, 1. So in a tie situation like that, you want to look at which of the two has the negative charge on the more electronegative atom. Question becomes, what's more electronegative, nitrogen or oxygen? Oxygen. So that's the best. Questions there? All right, let's move on a little bit then. Oh, by the way, could you give the resonance form of this? There's several of them, but ignore the ring for now. Give me the one for just the functional. So I have a question for you. To draw the other resonance form up, can we bring a lone pair from oxygen to carbon? I make a triple bond between carbon and oxygen. No. The reason I can't do that is because that would give that carbon too many bonds. I mean, I could do that theoretically if I had a pi bond that I could shift over. Remember, when we're drawing resonance forms, the only thing you can move are lone pair electrons and pi bonds. If I brought a pair of electrons down to make a carbon-oxygen triple bond, that is a sigma bond, and that is a sigma bond. I cannot move those. So if I just brought and made a third bond to carbon, then that carbon would have way too many bonds. So I can't do that. What I could do, however, is bring electrons, the lone pair, from nitrogen to carbon, because there's a pi bond I can break. And that's what I'm going to do. Question 6. Yeah, because remember, a normal nitrogen or a neutral nitrogen is always going to have 3 bonds and 1 lone pair. This has 4 bonds, no lone pair. So that tells me it's not a 0 charge. And you'll start to get a feel for this at the more that you work with it. But again, if you were unsure, like, okay, well, I know it's not 0, it's not a neutral nitrogen, but what is it? Do the formal charge calculation. Tell you that. Okay. Let's get into a slightly different topic. And we're going to look at some stuff with isomers. So as of now, we're going to look at 2 classes of isomers. The first of which are what are known as constitutional isomers. So constitutional isomer means it's 2 structures that have the same molecular formula, but a different connection of atoms. All right, so as an example, if I were to say C5H12, there are a few different isomers or structures, different structures I could draw with that formula. The easiest is always just draw it out in a straight line, 5 carbons in a row. So 1, 2, 3, 4, 5. There we go. That is one isomer of C5H12. I've got 2 more. What about this one? Is that a different isomer of C5H12? CH3, CH2, 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 CH3. CH3, CH2, 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 CH3. Those have the exact same connection of atoms. So those are not different structures. The way I got from here to here was simply through a rotation of that bond. So they're different rotational states, but structurally they are identical. When you go to start trying to come up with isomers, the way to do that is by starting to branch the parent chain. So instead of having 5 carbons in a row, maybe have it be a shorter chain with a branch, as an example. What if I had a 4 carbon chain? And then I put a branch somewhere. Like that. Now instead of CH3, CH2, 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 CH3, we have CH3, CH to CH3, CH2, CH3. put together in a different way. What about this one? That different. That's these two are actually identical, right? I just took this and flipped it over. Those are actually identical. I feel like I've got one more. Oh, what about this? That's the same as that as well. 1, 2, 3, 4 carbons with another methyl on carbon 2. 1, 2, 3, 4 carbons with a methyl group on carbon 2. Those are the same. So the point being that I can draw these in all sorts of directions, but just because it looks different doesn't mean that it is different. What's my third option here? That's going to actually give me a different compound. Anybody see? Yeah, kind of like an X. So I'm just going to take this one, that second one, and make it even more highly branched. So maybe instead of a 4 carbon chain, make it a 3 carbon chain with 2 branches. That would look like. So there's my 3 carbon chain. There's 1 branch. There's 2 branch. So those would be the 3 different constitutional isomers of C5H12.
That's not a stereoisomer. That's a single stack.
Yeah, it's not an isomer at all. Yeah, it's the identical compound. Because basically, I just took a molecule and kind of flipped it over, rotated it a little bit.
But then, it's kind of a future question. Just looking at the stereoisomers is like.
Yeah.
And so flipping it over is the same but different.
Don't worry about that for now. That we'll spend an entire chapter on that stuff, but not now. No. All of those are constitutional isomers. Because the definition of a constitutional isomer is they have the same molecular formula, but a different connection of atoms. We got a couple minutes, about 5 minutes left, so we can go ahead and I think that's the next thing we're going to talk about is the difference between constitutional and stereoisomers. Right. So as I said, a constitutional isomer, same molecular formula, different connection of atoms. All right. A stereoisomer, so actually let me go ahead and write that. A stereoisomer, on the other hand, is something that has the same molecular formula, same connection of atoms, but a different 3-dimensional shape. Or another way sometimes people will phrase it, a different spatial arrangement of atoms. Yeah. No. Because if I have it like this, or I have it like that, this is still CH3, CH, CH3, CH2, CH3. CH3, CH, CH3, CH2, CH3. It's the exact same connection of atoms. All I did literally was I took this guy and rotated it like counterclockwise. So, and probably the most common example of stereoisomers would be something we alluded to at the beginning, which was those cis-trans isomers. So with double bonds, because they don't freely rotate, if I have this form of the double bond, that is different from that form. And we give these names where the H's are kind of going opposite one another, like they are here, right? One H is going up, the other H is going down. We call that a trans conformation. Where the H's are going in the same direction, this one's going down, that's going down, that is a cis. But notice, think about our definition that we laid out a second ago. Stereoisomer has the same molecular formula. Those guys are both C4H8. They have the same molecular formula.
A molecular formula is an expression that states the number and type of atoms present in a molecule of a substance. This is from Socratic.
Someone's listening to me, apparently. Anyway, same molecular formula. They have same connection of atoms. CH3, CH, CH, CH3. CH3, CH, CH, CH3. The same connection of atoms. They just have a different three-dimensional shape or different spatial arrangement. That is a stereoisomer. The other time you kind of see this commonly, it most commonly crops up when you have a restriction of bond rotation. Right? That's what the double bond does. A double bond does not have freedom of rotation. So that means that in this particular conformation, the H's are opposite one another, and they will always be opposite one another. They cannot simply rotate like a single bond. Here the H's are on the same side of the molecule. They will always be on the same side of the molecule because, again, that double bond cannot freely rotate. The other thing that often restricts rotation in this way is a ring. So imagine something like this. Now, what you're going to see a lot of times, especially when you start to get into ring structures like this, are these wedges, kind of darkened lines. What that's trying to indicate is I'm trying to indicate three-dimensional structure in two-dimensional space. The ring is in the plane of the page. What that dash is indicating is that those two methyl groups are coming towards you. If I wanted to indicate that they were going kind of away from you into the page, I would indicate that with a dash line. So here, both of the methyl groups are coming towards you. Here, one of the methyl groups is coming towards, the other is going away. So if they're going in the same direction, this would be a cis ring. If they're going in opposite directions, that would be a trans. But they have the identical molecular formula. They have the same connection of atoms. 5-membered ring with a CH3 on carbon 1 and a CH3 on carbon 2. 5-membered ring, CH3 on carbon 1, CH3 on carbon 2. So the exact same connection of atoms. The different three-dimensional structure. So those are the two most common categories of stereo. They both arise due to a restriction of bond. Questions there? Okay, that is probably a good place to stop. What I would actually ask you to do, in the slides, I have these examples. So go ahead and with the two concepts we've just been talking about, constitutional isomer, stereoisomer, I want you to classify each of the three pairs as constitutional or stereoisomers, and we'll pick it up from there on Tuesday next week. All right. Have a good weekend.